everybody, the purpose of this video is to go over section 1 of chapter 2, and we will be talking about rectangular coordinates and graphs. Specifically, we're going to go over ordered pairs, reintroduce to rectangular our Cartesian coordinate system, introduce the idea of the distance formula and how that can be applied to determine right triangles and collinear points, the midpoint formula, and then we will conclude with graphing equations in two variables, specifically graphing quadratic equations in two variables. So let's start off with ordered pairs. Now, an ordered pair looks a lot like an open interval and interval notation, but it is not. Instead, it consists of two items written inside a parentheses. Those items can be numbers, they can be names, they can be practically anything. But typically in our course, since this is math, we will be dealing with numbers. So here are in ordered pairs that are consisting of real numbers, or in this particular case, actually integers. And of course, these ordered pairs are used to define relations, which is defined as a collection of ordered pairs, and functions, which basically are relations that are well defined. What does that mean? For every single x value, there is only one y value. Okay, and also remember, since these are called ordered pairs, yep, order matters. So 6, 2 is not the same thing as 2, 6. Okay, and this brings us to the rectangular coordinate system, or also known as the Cartesian coordinate system. And it turns out that there is a one-to-one mapping between each ordered pair and a point on the rectangular coordinate system, or the Cartesian coordinate system. Of course, this was the brainchild of René Descartes, who was a French philosopher between the 1500s and 1600s. Even though he was a French philosopher, he actually spent most of his time in the Netherlands, working, or at that time called the Dutch Republic, and he is dubbed the father of Western philosophy. Even though he's done a lot of work in mathematics, he's actually more known for his work in philosophy. However, much of his work in mathematics formed the basis for the work of Isaac Newton, particularly in the area of calculus. Unfortunately, he made the dreadful mistake of going to Stockholm, Sweden in 1650 to tutor the warrior queen, actually at the time, the warrior princess Christina, on his ideas of love. And that didn't work out so well. One, they hated each other. Christina could not stand him. And two, he was living in a cold, drafty campus, or a cold, drafty castle, and yeah, he died of pneumonia. So what else do I want to say about this one? Check out these quadrants. Notice the Cartesian coordinate system is broken out into four quadrants. This is the first quadrant, and in this quadrant, both the x value and the y value are positive. In quadrant 2, the y value is positive, but the x value is negative. In quadrant 3, both the x and the y values are negative. And finally, in quadrant 4, we have positive x values, but negative y values. And that will come in handy for this particular example. Suppose that we have a point and it lies in quadrant 2, and we're going to call this point AB. If AB lies in quadrant 2, then we know that A is negative and B is positive. And our first question is, well, then what quadrant does negative AB lie in? Now, there's a couple of ways to do this. One is we can just basically play the mind game with the signs, but it might be better to come up with an A and a B that actually resides in quadrant 2. Okay, well, if that's the case, A has to be a negative number, so how about negative 3? And then B has to be a positive number, so how about 2? Okay, so we have that A is equal to negative 3. Negative 3, that's kind of important. B is equal to 2. And if that's the case, then negative A is going to be equal to 3. And then negative B is going to be equal to negative 2. Okay, so if that's the case, then the coordinate negative AB is going to be the coordinate 3, 2. And what quadrant that lie in? That would lie in quadrant 1. Okay, what about A negative B? Well, A is negative 3. Negative B is negative 2. That's quadrant 3. Okay, since they're both negative. Okay, and what about negative a, negative b? Well, negative a is 3. Negative b is negative 2. That's quadrant 4. And now we're going to pull a fast one on you. What if the first coordinate is negative b? Well, that means that the first coordinate would be negative 2. The second coordinate, well, that's a, which is going to negative 3. That will be negative 3. Well, two negatives, that's quadrant 3. So that's a great way to deal with this problem when you see it once or twice in your homework. Also in this homework, you are going to have to find x and y intercepts for particular graphs. Now the x-intercept is that value of x when it crosses the x-axis. And it crosses the x-axis when y is equal to 0. So what we want to do is set y equal to 0 and solve for x. And if we do, we will have 6 times x plus 2 times 0, which is 0. And that's going to be equal to 12. And that means that x is equal to 2. So the x-intercept is this point right here. Now remember, to describe that particular point, you need to use an ordered pair. And the first coordinate, the x-coordinate, of course, will be 2. But the y-coordinate, since we are on the x-axis, will be 0. And this would be the answer you put into MML. In this particular course, you will describe x-intercepts and y-intercepts not by this particular number, or this number for the case of y-intercepts, but as an ordered pair. So this brings us to the y-intercept. Now in this particular case, we want to find that value of y where it crosses the y-axis. That occurs when x is equal to 0. In that particular case, we're going to have 6 times 0, which is 0, plus 2y is equal to 12, and we will have that y is equal to 6. So and we can't really plot that because I only go to 1, 2, 3, 4, 5, 6, I guess, suppose is up here somewhere. So that coordinate, once again, is going to be the x value, which is 0, and the y value, which is 6. And that is, once again, how you would put it into MML. Okay, now we want to talk about the distance formula, the idea of the distance between 2 points on a Cartesian plane. And this actually is an application of the Pythagorean theorem. So here we're going to let p x1 and p x1 y1, or p and q be two distinct points. P will have coordinates x1 y1, q will have coordinates x2 y2. And the distance between p and q will be given by this particular formula. This is the distance of the x-coordinate squared plus the distance of the y-coordinate squared, and we're going to take the square root. Okay, and as I mentioned before, this is an application of the Pythagorean theorem. However, I do have one question. What does distinct mean? Well, basically, distinct means different. That's all it means. Can't be the same point. Well, it could be the same point, but then the distance would be 0, which is not really all that interesting. But basically, when we say distinct, that's just a beautiful word for different. Okay, so what do you have going on here? Well, here's a quick example. Here is P, and here is Q. Now, notice that we can actually form a right triangle. And this leg is the change in the x value, and this leg is the change in the y value. So of course the hypotenuse is the distance, and that's all that we're doing here. That's all that is all that we are trying to apply. Okay, so let's go ahead and apply this to an example, and here we go. So here we want to find the distance between P, which is located at -8, 4, and Q, which is located at 3, -2. Now, okay, you can use the distance formula, okay, and that will be x1 minus x2, which would be -8 minus 3, which is equal to 11, and then we would have y1 minus y2, which would be 4 minus a -2, which would be 6. You can do that, or you can also draw a picture. So here's a picture of these 2 points on a graph. And notice the difference in x. Well, that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, just like we figured out. And then 1, 2, 3, 4, 5, 6 for the change in y. And then if that's the case, then the distance is going to be between P and Q is going to be the square root of the difference in the x values, which will be 11 squared or 121, plus the square root of the change in y values, which will be 6 squared or 36. and that will be equal to the square root of 157. Now, if you're asked for the exact answer, this would be it. This is the exact answer. If you're asked for an approximation, that means you need to break out the calculator and find the square root of this, and if you did, you would find that this is equal to 12.530 down to the third decimal place. Now, one application of the distance formulas is that we can use it to determine whether a triangle is or is not a right triangle. Okay, so let's always we have A, B, and C, and these are the sides of the right triangle. The Pythagorean theorem states that a right triangle with sides, or a triangle with sides A, B, and C is indeed a right triangle if and only if A squared plus B squared, i.e. the sum of the square of the shorter sides, equals the square of the distance of the third side. Okay, what does that mean? Well, if I tell you that this thing is a right triangle, and this has to do with the if and only if part, if I tell you that the triangle is a right triangle, then you know for a fact that the sum, that A squared plus B squared equals C squared. If I tell you that I have a triangle where this relationship is satisfied, where A squared plus B squared equals the square of the third side, then, not they, but then that triangle must be a right triangle. And we can use this to solve this particular problem. So we have these points, M negative 2, 5, N located at 12, 3, and Q located at 10, negative 11. And we want to know, are these the vertices of a right triangle? Well, to do this, to figure this out, we would need to compute the square of the distance of the square of the three distances between these points. Okay, so let's go ahead and do that. Let's first take a look at the square of the distance between M and M. That is going to be equal to 12 minus negative 2 squared, and that's change in x, plus 3 minus 5 squared, and that will become 14 squared, or 196, plus 2 squared, which is 4, and that will give us 200. So the square of this distance is 200. Okay, let's take a look at d squared, the distance squared between M and Q. Okay, that will be 10 minus negative 2 squared plus negative 11 minus 5 squared. That will give us 12 squared, which is 144, plus 16 squared, which is 256, and that will be equal to 400. So this appears to be the larger leg, and if you look at our picture, yeah, it is the larger leg. So right here, this is 400. So if this distance is, if the square of this distance is 200, then it's a right triangle. If it is not, then it's not a right triangle. So let's figure that out. D squared, the square of the distance between N and Q, that is going to be 10 minus 12, 10 minus 12, entire thing squared, plus negative 11 minus 3. Okay, well, 10 minus 12 is negative 2, squared is 4. Okay, and negative 11 minus 3, well, that's 14, and square of that is 196. And that equals 200. So we have that a squared plus b squared is equal to 200. Let me see, put 200 over here. Plus 200, which is equal to 400, which is equal to c squared. This is a right triangle. Now we can also use the distance formula to determine if 3 points are collinear. And how can we do that? Well, it turns out that if 3 points are collinear, then the distance of the two smaller points or the distance of the the two shorter distances will add to the longer distance. If the two shorter distances is greater than the longer distance, then they are not collinear, and there's no way the two shorter distances can actually be less than that, or that just simply wouldn't work out. Okay, so if here we have basically 3 points, and once again, if this distance and this distance adds to this distance, they are collinear. If they don't, then they're not. So let's actually see an example of that, and we will use this. And once again, we're going to draw a picture. Now, many cases, they may give you a situation where they look like they're pretty close to collinear, but they may be off, so the picture can be deceiving. So even though they look like they are collinear, it might be good to do the math just to make sure. Okay, so once again, to do this, we need to take the distance, we need to compute all three distances between P and Q, between P and R, and between Q and R. So let's take a look at the distance between P and Q. And since we're actually looking at distances and not squares, we actually do need to take a square root. So the distance between P and Q is going to be the change in x's, which will be 2 minus -1, that entire thing squared, plus the change in y, which would be -4 minus 5, the entire thing squared, and we're going to take the square root of all of that. Now if we do, we will come up with the square root of 9 plus 81, which is equal to the square root of 90. And we'll just leave it like that for the time being. Now the distance between P and R, and as you can tell by the picture, this will be the longer distance. That is going to be equal to 4 minus -1, the entire thing squared, plus 10 minus 5, -10 minus 5, I apologize, -10 minus 5, the entire thing squared. And we're going to take the square root of that. Well, 4 minus -1, that actually is 5. 5 squared is 25. Okay, 10 minus -5, that is -15. Squared is 225. And that is the square root of 250. And then finally, we have the distance between Q and R. And that is going to be 4 minus 2. The entire thing, that quantity squared, plus -10 minus -4. The entire thing squared. Take the square root of that. Of course, 4 minus 2 is 2. Squared is 4. -10 minus -4 is -6. Squared is 36. And that gives us the square root of 40. So now we need to see if the two smaller distances, this one and this one, actually sums to the larger distance. So we are going to have the square root of 90 plus the square root of 40. Now we can write this we can actually take out a perfect square, because 90 can be written as 9 times 10 square root, and then 40 can be written as 4 times 10 square root, and that will give us 3 root 10 plus 10, not 2, plus 2 root 10, which will give me 5 root 10. And it turns out that that the larger distance, which is 250, I'm getting ahead of myself, we can write that as 25 times 10. And the square root of 25 is 5, so this becomes 5 times the square root of 10. So it turns out that the sum of the two smaller lengths adds to the longer length, so this is indeed collinear. Okay, next we have the midpoint formula. Let's let P and Q be the endpoints of a line segment with these two coordinates. Then the midpoint of this line segment will have the following coordinates. The x-coordinate will be the average of the two x-coordinates, and the y-coordinate will be the average of the two y-coordinates. And that's pretty much all there is to it. So in this case, the x-coordinate is going to be the average of -8 and 4, which is -2. And the y-coordinate is going to be the average of 4 and -2, which happens to be 1. Okay, so one example will be, here's one example that you'll see in your homework here. We need to find the coordinates of the midpoint of the line segment with endpoints 8, -4, and -6, 1. Okay, so what we want to do is we want to find the average of the x-coordinates. So for the x value of the midpoint, that is going to be the average of the x-coordinates, which is going to be 8 plus -6 divided by 2, which will be 1. And then for the y value of the midpoint, it's going to be the average of the y-coordinates, which is going to be -4 plus 1 divided by 2, which will give us -3/2. Now, does that make sense? So our point is going to be 1, -3/2. Does that make sense? Well, here's 1, there's -3/2, and that pretty much looks like it's in the middle to me. Now, one of the things that we're going to see is we're going to be given a midpoint, we're going to be given one endpoint, and we need to find the other endpoint. Now, is that insurmountable? Well, of course not, because remember the x value, the x coordinate of the midpoint is found by taking the midpoint, the x value of the midpoint, which is 8, and computing the average of the two endpoints, which is going to be -6 plus x2, since we don't know what that is, divided by 2. Okay, and then the y coordinate of the midpoint, well, that's -2. That's found by taking the average of the y coordinates, which will be 12 plus y2, whatever that is, divided by 2. We just solve for x2 and y2, and if we do, we will have 16 is equal to -6 plus x2, and x2 will be 22, and then -4 will be 12 plus y2, and y2 will be -16. And so our coordinate for the endpoint is going to be 22, -16. And if we plot that, oh, here it is. And as you can see, it works out just fine. Now, you will have a number of applications with midpoint formulas, and this is an example of one of them. Here the following figure depicts how a graph might indicate the increase in revenue generated by fast food restaurants in the United States from $69 billion in 1990 to $164.8 billion in 2010. And we want to use the midpoint formula and the two given points to estimate the revenue from fast food restaurants in the year 2000 and compare it to the actual figure of $1.07 billion. Well, notice we have 1990 in the x-axis and 2010 in the x-axis, and the x value of the midpoint therefore will be 2000. So all we need to do is figure out the y coordinate of the midpoint, and that's just a direct application of the midpoint formula. It's going to be 69.8 plus 164.8 divided by 2. And if you knock that out in your calculator, you are going to have 117.3, which is what you would put into MML. Now, the last thing we want to talk about are finding ordered pair solutions for equations and graphs, and then graphing that equation. So here is our example. For the given equation, we want to find at least 3 ordered pairs that are solutions to the following equations, and we want to graph that equation. And here it is. We have y is equal to x squared minus 6. Okay? So basically we want to fill out the y coordinate for this table. And if we do, well, if x is 2, x squared is 4. 4 minus 6, well, that's -2. So we will put in -2 here. When x is 0, well, we're going to have 0 squared, which is 0 minus 6. We'll have -6. And then finally, if x is 2, x squared is 4, minus 6, we have -2. Okay, once you've done that, you're going to be asked to graph the equation in MML. And this is how you do it. Okay, when you get to MML, you will see something like this. Okay, and what you want to do, there's actually two ways of doing it, but the way that I prefer to do it is don't click this because it gives you a large graph, but it's one size and one size only. So, but what you can do is you can click this, and you can make the graph as big as you want. Okay, once you've done that, you need to click this tool right here, which is called the 3-point quadratic tool. Okay. Now, if you remember, I'm going to go back to my to the slideshow. We have -2, -2, 0, -6, and 2, -2. We need to plot those numbers. So what you would do is we would go to -2. We would go to -2, -2, click there. Go to 0, -6, and click there. And then go to 2, -2, and that is how we will plot our particular function. Okay? Now, and if I click check answer, and that was the equation that was asked to solve, it would say that I'm correct. Now, unfortunately, we are being asked to figure something, we're being asked to plot this particular equation, and as you can see, I've gone ahead, I figured out the y values. Here the equation is x squared minus y is equal to x squared minus 4. When x is equal to -2, x squared is 4, minus 4 is 0. And then when x is 0, y is going to be -4. And then when x is 2, y will be 0 again. So now I'm going to go ahead and plot this function so you can see how the interface works for the entire problem. So I need to plot these 3 points. One is -2, 0. The other one is 0, -4. And once again, remember, I press the quadratic tool, and the last one is 2, 0 right there. Okay, so I've done that. I can click check my answer, and there it is. And that is pretty much how that particular problem works. And of course, it is highlighted in this example right here with these particular steps. Just remember, that's the tool that you want to use. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.